Download this code from codegive.com, link in the description below. OK, let's dive deep into solving the traveling salesman problem, TSP, using branch and bound. We'll focus on the 7-city/3 salesman scenario, providing a detailed explanation, pseudocode, and a Python code example. 1. Understanding the traveling salesman problem, TSP. The TSP is a classic combinatorial optimization problem. Given a set of cities and the distances between each pair of cities, the goal is to find the shortest possible route that visits each city exactly once and returns to the origin city. 2. The 7-city/3 salesman variation, 7-3 TSP. This is a more complex variant. Instead of a single salesman, we have 3 salesmen, and the task is to divide the 7 cities, including the starting city, into 3 tours such that each city is visited exactly once and the total distance covered by all 3 salesmen is minimized. Important considerations for the 7-3 TSP **** starting city * all salesmen must start and return to the same depot or starting city. * constraints * each city must be visited by exactly 1 salesman. * each salesman must start and end at the depot. * no subtours are allowed. A salesman can't visit a subset of cities and return to the depot without visiting all the assigned cities. Complexity * the 7-3 TSP is significantly harder than the standard TSP due to the additional layer of partitioning the cities among the salesmen. 3. Branch and bound, the core idea. Branch and bound is a systematic search algorithm for solving optimization problems. It works by branching * dividing the search space into smaller subproblems, branches. Bounding * calculating a lower bound, optimistic estimate, on the cost of the best solution achievable within each subproblem. Pruning * eliminating subproblems that are guaranteed to be worse than the best solution found so far, incumbent solution. 4. Implementing branch and bound for the 7-3 TSP. Here's a breakdown of the steps involved. 4.1 Data representation * distance matrix * A2D array, or matrix, distance _ matrix ij stores the distance between city I and city j. Since it's the TSP, we'll assume the distance from a city to itself is 0, distance _ matrix ii equals 0. Cities * an array or list containing names or IDs of the cities, including the depot. Salesmen * an array or number representing the number of salesmen, in this case, 3. 4.2 Node representation * Each node in the branch and bound search tree represents a partial solution. We'll need to store the following information for each node. Assigned _ cities, a list of lists. Assigned _ cities I contains the cities assigned to salesman I. Initially, all assigned _ cities lists are empty except for the depot, which is the starting point for each salesman. Unassigned _ cities, a list of cities that have not yet been assigned to any salesman. Cost, the cost of the current partial solution, sum of distances traveled by all salesmen so far. Lower _ bound, a lower bound on the cost of any complete solution that can be derived from this partial solution. 4.3 Branching strategy *. The branching strategy determines how we divide a subproblem into smaller subproblems. A common strategy for the TSP is to 1. Select an unassigned _ city. 2. Create a new node for each salesman. 3. In each new node, assign the selected unassigned _ city to a different salesman. Example *. Let's say we have unassigned _ cities equals city 2, city 3, and we select city 2 for branching. we would create 3 new nodes. Asterisk node 1 asterisk assigned underscore cities 0 dot append, city 2 is assigned to salesman 1. Asterisk node 2 asterisk assigned underscore cities 1 dot append, city 2 is assigned to salesman 2. Asterisk node 3 asterisk assigned underscore cities 2 dot append, city 2 is assigned to salesman 3. The process is repeated for the next unassigned underscore city until all cities are assigned. 4.4 Bounding function asterisk. The bounding function is crucial for pruning. It must provide a lower bound on the cost of any solution that can be obtained by expanding the current node. A well-designed bounding function significantly improves performance. Here's a bounding function approach adapted for the 7-to-3 TSP. 1. Cost of partial solution asterisk. Calculate the cost of the partially constructed tours for each salesman. This is the sum of the distances between cities already assigned to that salesman in the order of assignment, including the return to the depot. 2. Minimum spanning tree, MST, heuristic asterisk. For each salesman, construct a minimum spanning tree, MST, for the unassigned cities and the last city assigned to that salesman, or the depot if no cities have been assigned yet. The cost of the MST provides a lower bound on the cost of connecting the unassigned cities and returning to the depot for that salesman. Asterisk note asterisk. You'll need an MST algorithm, example Prim's or Kruskal's algorithm. 3. Summation asterisk. Sum the cost of the partial tours and the MST costs for all salesmen. This sum gives a lower bound on the total cost of completing the tours from the current partial assignment. 4.5 Pruning asterisk asterisk. Compare the lower underscore bound of each node with the cost of the best solution found so far, the incumbent solution. If the lower underscore bound of a node is greater than or equal to the incumbent cost, then that node and all its descendants can be pruned, eliminated from the search. 4.6 Algorithm outline, pseudo-code. 5. Python code example asterisk asterisk. Explanation of the code asterisk. 1. Calculate underscore tour underscore cost asterisk. Calculates the cost of a single salesman's tour, including returning to the depot. 2. Minimum underscore spanning underscore tree underscore cost asterisk. Calculates the cost of a minimum spanning tree. This provides a heuristic estimate of the distance needed to connect all remaining cities. 3. Calculate underscore lower underscore bound asterisk. Calculates the lower bound for a given node, summing the cost of the already constructed tours and the MST cost for unassigned cities. 4. Solve underscore 7 underscore 3 underscore teaspoon asterisk. Asterisk initializes the root node with empty tours, except for the depot, and all cities as unassigned. Asterisk uses a priority queue, heap, to store nodes, prioritizing nodes with lower bounds. Asterisk the while loop continues as long as there are nodes in the queue. Asterisk nodes are pruned if their lower bound is greater than or equal to the best solution found so far. Asterisk when a node has no unassigned cities, it represents a complete solution, and its cost is compared to the best solution. Asterisk branching, for each unassigned city, new nodes are created by assigning the city to a different salesman. The lower bound of each new node is calculated, and the node is added to the priority queue if its lower bound is promising. 5. Example usage asterisk creates a sample distance matrix, defines the cities and number of salesmen, and calls the solve underscore 7 underscore 3 underscore teaspoon function. The result is then printed. Key improvements and considerations asterisk. Asterisk more sophisticated bounding asterisk using more advanced bounding techniques like the held carp bound or linear programming relaxation can drastically improve performance. These bounds are more computationally expensive to calculate but can prune more branches. Asterisk branching strategies. Asterisk instead of simply selecting the first unassigned city, you could use more intelligent branching strategies, such as selecting the city that is farthest from the depot or the city that would most increase the cost of the partial tour. Asterisk heuristics for initial solution. Asterisk before starting the branch and bound search, you can use a heuristic algorithm, example nearest neighbor, to find an initial solution. This provides a good upper bound on the cost of the optimal solution and can help prune branches early in the search. Asterisk symmetry breaking. Asterisk in the 7-3 TSP, there might be symmetries. For example, swapping the tours of two salesmen might lead to the same solution. Techniques to break these symmetries can improve efficiency. Asterisk data structures. Asterisk choose appropriate data structures for the distance matrix, tours, and priority queue to optimize memory usage and performance. Asterisk complexity. Asterisk the branch and bound algorithm, even with good bounding, can still have exponential time complexity in the worst case. How to run the code. Asterisk 1. Save. Asterisk save the code as a Python file, example teaspoon_7_3.py. 2. Install heapc. If needed, the heapc module is usually part of the standard Python library, so you probably don't need to install it. 3. Run. Asterisk execute the script from your terminal, python teaspoon_7_3.py. The code will then print the best solution found and its cost. This detailed explanation and the Python code example provide a solid foundation for understanding and implementing the branch and bound algorithm for the 7-3 traveling salesman problem. Remember that the performance of the algorithm is highly dependent on the bounding function and branching strategy. Experiment with different techniques to find the best approach for your specific problem instance. Good luck.